Tim has now left the peer program and is working at RMS.
Thank you, Jay. I'd like to thank Jay and the ERI team to put together this seminar, and thank you for attending. I will be overviewing what we added in terms of records to the Grand Motion database from the NGA 1 to the NGA West 2 project. I'll overview the working groups that were involved with collecting and delivering the final product of the database, and then a quick summary of the key metadata changes between the two projects, NGA 1 and NGA West 2. So again, to overview what Yusuf said, this is a graphic to illustrate the NGA West 1 database that was available at the end of that project. It is shown here in a scatter plot of the magnitude versus closest distance to the rupture plane. The total number of records in this database was about 3,500 records. And so I have a very top here a notation indicating RSN. That's the record sequence number, or the unique identifier of each record added to the database. So as you add a record, you increase in sequence the number called RSN. And the NGA West 2 project, near the end of 2012, we added significant worldwide events to the database, and now you can see the new red dots illustrate that set of ground motions. The last event that was added to this data set was the February 2011 Christchurch event in New Zealand. At the very end of 2012, we finally added the small to moderate magnitude events from California. And now the total RSN in the database extends up to 21,000 records. So to give you a sense of where the events are located around the world, I have a plot of the hypocenter locations on the world map. And so I have two color schemes here. The NGA West 1 events are shown in blue. NGA West 2 events are shown in red. And so you can see from this graphic, there was a large set of events from Italy, one event from Iran, a large magnitude events in China with 64 aftershocks, 4 events in Japan, 2 events in New Zealand, and a couple of events that occurred in California and Mexico. So I'd like to blow up a certain region to illustrate that many of these new events are very well recorded. And so this is the area of China and Japan, and I have 2 events illustrated here. So for on the left, I have the hypocenter location for the magnitude 7.9 Winchuan event in 2008. And in the purple triangles, I have the stations that were recorded during that event. So the total number of records are listed here. So it's a large set of events large set of records for this event. And again, for the 4 events in Japan, I have one of those events, which is a magnitude 6.8 Chuetsu Oki event in 2007. And the blue triangles illustrate the locations of the recordings for that event. And so there are a total of 600 recording stations that were collected from that event. And so a large number of events in, say, the post-2003 era are recorded by these modern digital seismic networks, and you get a large set of recordings for each event. And to note, again, as Yusuf said, there was a couple of events that were significant in other regions, the 2 events in New Zealand from the Canterbury earthquake sequence, and then the L'Aquila event in Italy and the BAM event in Iran. So I have here a graphic to illustrate where the events were located for the small to moderate magnitude database that we collected in California. These are events with a magnitude less than 5.5 and at a magnitude greater than 3. We collected a huge set of records from a large, I would say, about 400 events. But after record processing and filtering, we ended up with 266 events with about 13,000 3-component records. And so this is a hypocenter location plot of those events that are now included in the NGA West 2 database. And the size of the open circle denotes the magnitude. And I'd like to thank here the 4 data providers that we collected data from. So the USGS Strong Motion Network, the Berkeley Digital Seismic Network, California Institute of Technologies Network, and the California Geologic Survey. So Without their support and their help in collecting this records, we couldn't have collected the data and created the database. So in total, combining the NGA West 1, the new significant worldwide events, and the new California small to moderate magnitude events, we have what we call the NGA West 2 database. And that composed of about 600 events with 21,000 three-component records. And I have here approximately 21,000 records because many of the times, the older records, we didn't have all three components. The magnitude, the closest distance to the rupture plane, and the VS30, their time average shear wave velocity, the upper 30 meters, the data range is shown here. And so there's a significant now improvement in the data range, but at far distances greater than about, I think, 12,000 kilometers, the data becomes very thin. And at very hard sites with VS30 greater than about 1,200 meters per second, it also becomes very thin. So after illustrating what we collected, I'd like to go over the working groups that were involved in this data collection effort and processing. I break the discussion up into the various topics that were focused for different fields of expertise. So the first working group was the source working group. They were responsible for reviewing all the event parameters that were compiled into the database and then as well into the flat file. And then we had a path working group, which was responsible for calculating all the path metrics and the directivity parameters. We had a site working group. The main responsibility was creating what we call a site database, and I'll overview what that is and the main components of that database. And then we had a large record processing group, which had the main responsibility of collecting the records and processing and filtering the time series. And in the end, after all of the records were processed, all the event parameters, site parameters were collected, we had an effort to compile all that key information into what we call a flat file for the ground motion modeling development. So for the source working group, I have the set of participants listed. It composed a large group of seismologists, and so I have a couple tasks that I'd like to overview, which that they were responsible for. So the first task that I'd like to discuss is the compilation of the finite fault solutions for the events in the NGA West 2 database. So what they did was they reviewed the available finite fault solutions from the literature for the events that were collected, and then they compiled all of those finite fault solutions into an internal source table. I have a graphic at the bottom to illustrate some of the parameters that they were also interested in addition to just the fault geometry. So I have the depth to the top of the rupture, the rake, the strike, and the dip. And so in many cases, there were multiple finite fault solutions for the events selected. So there was a preferred methodology proposed, a way to select the preferred finite fault solution for these events. And so it was based on the method of inversion used and the data that was used in the inversion. So the details are in the NGA West 2 database report. In many cases, there was no finite fault solution available, and then for the small to moderate magnitude data set in California, all of the events did not have a finite fault solution. So in this case, there was a methodology to simulate a finite fault plane. For these events, we collected the moment tensor solution information, the strike, dip, rake mechanism, and the hypocenter location. And then we sampled, we generated 101 simulated geometries, and we calculated the closest distance range from those geometries to a set of pseudostations. The idea is that we don't know where the hypocenter is located on the fault plane for these events, but with this set of pseudostations, we can calculate an average fault plane in space relative to its hypocenter. And so what we do is we shift, tilt, and spin based on probability distributions of the aspect ratio, the hypocenter location, and then we select the fault plane that best fits the median closest distance range for those set of pseudostations. The idea of using a set of pseudostations is that when we add or remove a station in the recorded group of stations, we can change the simulated fault plane geometry. And so using a pseudostation network, we don't have to change this simulated fault when we add or remove a station. The next working group I'd like to overview is what we call, the two last tasks for this working group I'd like to talk about is two important things. One is the multi-segment event parameters that are assigned into the flat file, and then a very important task which was the event classification, or whether or not it's a main shock or aftershock in the ground motion modeling development. So in the multi-segment rupture case, there are two cases considered here. One is a multi-segment case where you have a continuous fault plane that's joined as you go down, as you extend the fault plane down dip, and we call this a multi-segment rupture. And then we have a second case called a multi-fault rupture where you have non-continuous segments, and for those each segment has its own independent hypocenter. And so the color scheme here shows which events are in each case, and this is a complete set of multi-segment cases in the NGOS2 database. So for this affects the event parameters that are listed on the flat file. So I have a list here of what some of the event parameters that we had to consider in this project. One was the hypocenter location. So for the multi-fault case, we had to select the hypocenter location that was thought to initiate the rupture. And for the rake and the area, it was based on simple summations and weighted averages based on the area. The last two items that are in bold are two new metrics that are added in the NGOS2 database. One is a local strike direction, which is the average strike within of the segment within 20 kilometers of the station. And then we have segment-dependent event parameters, segment dip and segment rake, which is the dip and the rake to the closest segment to the rupture. And I have a note here, the magnitude 7.1 DAR field event was a multi-segment, multi-fault rupture, but in the NGOS2 database, we didn't have a complex finite fault solution for this event. And so we will be updating the finite fault solution for this event in the next iteration of this project. The last task for the source working group was to assign event classifications for all the events in the NGOS2 database. And the event classification is quite new. It was a procedure proposed by Waddell and Abramson, it was discussed and revised within the ground motion modelers developers. And I have a graphic here to illustrate how this is done. So the idea is that we assign classification numbers to each event. So classification number 1 would correspond to main shocks, aftershocks, triggered events, and foreshocks, and that are not, say, in close proximity in time to a previous rupture. The class 2 events are events in close time in close proximity in time and space to a past rupture surface. So the idea is that we want to assign a class 2 event to an event that ruptured the same fault plane that the main shock occurred on. So the two windows that we used, in the time window, we used the Garner-Knopf time window, and then the space window, they developed a new window, what we call the CRJB window, or centroid, the centroid of the surface projection of the potential class 2 event to the surface projection of the class 1 event. And so the graphic here on the right illustrates this CRJB distance. I have four fault planes illustrated in the dashed black lines. The large fault plane is the class 1 event, and it has a hypocenter shown in the yellow star. And then I have 3 potential class 2 events. The centroid of each of those potential class 2 events are shown in the circle with the cross in it. And then we can calculate the CRJB distance from that centroid to the main shock surface projection. And so those are shown in the blue and the blue arrows. So we have 6 distance windows that were considered in this classification scheme. And so for example, if we used a distance of 0, only one of the events would be classified as a class 2 event. And that would be the one with the CRJB distance of 0. The second working group was a path working group, and I have the participants listed here. One of the main tasks was calculating the path metrics, and so I have a graphic illustrating the well-known path metrics. the hypocenter distance on the left and the closest to the rupture plane on the left. And then I have on the right a profile view of a dipping fault plane and the joiner bore distance and the epicenter distance in red and blue respectively. Two new path metrics were added to the NGAOS2 flat file. These were called RY and RX. RX is not new. It was proposed in one of the NGAOS1 equations, but now it is listed for all the records in the NGAOS2 database. So I have a graphic to illustrate what these two metrics are. If I take on the very far left, I have a very simple fault, which is a single plane fault, and then the gray area is the surface projection of that event. If I have a circle denoting the top center of that fault, we can calculate RY and RX from that point. RX is the strike normal direction from that point. RY is the strike parallel distance from that point. And so for simple faults, you can calculate this quite easily. Single faults, I mean, single segment faults. But for multi-segment faults, this is quite complex due to mainly the bend in the geometry, and in some cases for the multi-fault case where you have overlaps of the fault plane. And so for those cases, we used a generalized coordinate system that was developed by Brian Chu and Paul Spudich. They updated it for this project, and I have a graphic to illustrate how that works. So what the generalized coordinate system does is it calculates a U and T distance parameter, and the graphic on the left illustrates the U and T for a simple fault case. So what it is the same kind of metric. It's now measured from the top left edge of the fault plane, and so U is the strike parallel direction, and then T is the strike normal direction. So the multi-fault case, what this calculation does is it allows a smooth transition of these U and T parameters along the fault that bends in space, and then in between, say, faults that are overlapping. So I have a case on the right to illustrate what that does. I have a contour plot of U for the 1971 San Fernando earthquake with the two fault planes shown in the dashed black lines. And so I have the top left edge shown in the red, and then the direction of where U would increase. And so it's hard to see up here on this graphic, but on your sheets you can see that the contours bend in between the two fault planes in a smooth fashion. And so you can calculate RX and RY from these the U and T. And that's what was done for these multi-fault cases. The last thing that this working group was responsible for was calculating new directivity parameters. These directivity parameters are summarized in a peer report by Spudich et al., and that is available on the peer website. And so I have a list of the available directivity parameters that are now on the flat file. We have an update of the Spudich and Chow directivity parameter in 2008. We have two parameters from the Batty-Rochandel's model, and we have two parameters from the Shrey, Shahi, and Jack Baker model. The third working group I'd like to discuss is the site working group. Their main responsibility, as I said, was to develop what we call the site database. It was a collection of all the information for each of the recording stations. The main information that they were interested in is the VS30 and a basin depth parameter. The basin depth parameters here I listed are the Z1 and Z2.5. They're the depth to a shear wave velocity horizon. So for Z1.0, it is the depth to the shear wave velocity of 1 kilometers per second. In the efforts of collecting this information, they were concerned with collecting the VS from measured profiles. And so I have a graphic here to illustrate the result of that effort. So for the NGAOS1, I have a list of the number of stations for different regions, and shown in the left. And so if you go from the far left to the right, we have China, Japan, Mediterranean, all other regions grouped together, and Taiwan, and then California on the right, shown in the green bar. So these bars illustrate the number of stations from those regions that had a measured VS profile, or shear wave velocity profile. The bar above that indicate the number of recording stations in the database that were that did not have a profile, but we had to infer a VS30 from. And so I have a couple slides after this to illustrate how we estimated these inferred VS30 values. But if you compare the NGA West 1 on the left to the NGA West 2 on the right, you can see there is a large number of recording stations that now have VS profiles for Western North America or for California, and then in Japan. So for when we didn't have a VS shear wave velocity profile, we had to estimate VS30 from various correlations. And those correlations are from, say, surface geology or topographic slope. And we call these proxy estimates of the VS30. So I have listed here the number of proxies that were collected for the recording stations in the NGA West 2 project. And then a quick note here is the two top ones, which are not bold, those were included in the NGA West 1 project. The three ones in bold, the ground slope, the terrain, and the hybrid approach, are new and were collected in the NGA West 2 project. In addition to collecting these proxy estimates for each of the recording stations, we had to assign the uncertainty value in each of the ways to estimate VS30. And so this is a graphic to illustrate that uncertainty for the various ways to estimate VS30. This is the graphic for NGA West 1, and the key thing here is on the very far left, you have the uncertainty for when you have a measured shear wave velocity profile, and as you go for the far right, you have the inferred methods. And you can see how the uncertainty will increase as you have less information about the shear wave velocity. So this is an updated graphic of that same plot. This is the sigma for each of the methods, or the uncertainty for each of the methods. And again, on the very far left, you have the methods with using the shear wave velocity profile, and on the far right, you have the proxy estimates. So the key things to note here is that for when you do have the measured shear wave velocity, we have now a lower estimate of the uncertainty. But when you go to the proxy estimates, you have a higher uncertainty, but none of the proxies perform better than the others. So there was a method to select the VS30 based on the uncertainty in the proxy method, and that method is described in the peer NGA West 2 peer database that's available at the peer website. So in addition to collecting VS30, the site database has the Basin depth parameters. This is the Z1 and Z2.5. These values are collected from community velocity models. And so we have three regions that we collected this from. One is the Southern California region, where we had two community velocity models from SCEC. On the left bottom, I have a plot of the stations that were within the velocity model from Shaw and his group at Harvard. And the color scheme for this plot illustrates the depth or the Z1.0 value, or the depth of that basin, essentially. And so if you go from blue to red, you get a higher depths in that basin. And if you go on the far right, we have a second, or an alternative model from Harold Magistrali and his group. They're called the S4 model. And so the number of stations is smaller within this group, and it's shown on the right. For the Northern California and the Bay Area, we had a USGS velocity model. We pulled information from that model, but I don't have a graphic for that. And then also for Japan, we had a velocity model from NIED. And then the stations again are shown to the graphic to the right. So after collecting the information about the station locations, the source information, we had a large working group at the same time processing all the ground motion records that were collected for the NGA West 2 database. In addition to the record processing, this group was responsible for calculating the rotated spectra, the ROT-DNN, that's now used in the NGA West 2 ground motion models. And then I'd like to go over some of the key, say, reasons of why we updated the processing methodology and some of the key changes between the NGA West 1 and NGA West 2 in terms of record processing and record quality. So first, I have a couple slides on illustrating what ROT-DNN is. Again, this is just to show, to reinforce what this metric is. And this was a metric proposed by Dave Bohr in 2010. ROT-DNN is calculated by combining the two orthogonal horizontal components into a single component, and then rotating that across all non-redundant angles over 0 to 180 degrees. And you calculate the response vector for each of those rotation angles. Then you sort the response vector in terms of amplitude, and we pulled out three fractals. The minimum, or NN equals 0, the median, NN equals 50, the maximum, or NN equals 100. The D in the row NN stands for that it is period dependent, as Yusuf said. And I have two graphics here to illustrate what this is. So I have an oscillator response of the Chalom Array number 5 recording from the 1966 Parkfield earthquake. And you can visually pick off from the oscillator response the Rot D100 value and its azimuth. And so I have here for a oscillator period of 1 second, a red line indicating the azimuth for the Rot D100 spectral amplitude. And if I go to an oscillator period of 2 seconds, you can see how and now in green, I have the azimuth of the Rho D100 illustrated, and you can see how it's different from the oscillator period of 1 second. So each period will have an independent rotation angle, and each of those rotation angles are collected. As Yusuf said, there was a large effort to reprocess all the ground motion records from the NGOS1 database. And in this effort, it was mainly due to a couple of reasons. One was that we selected a new filtering, a new preferred filter, which is an A-causal filter. The reasons for that is discussed in the NGOS2 database report. And then we also have an expanded period set. And so I have a graphic to illustrate the difference in the period sets between the two projects. On the bottom, I have the NGOS1. On the top, I have the NGOS2. The red triangles illustrate the periods that are now new in the NGOS2 database. So we have about the same sampling across the decades, but we've increased the density of sampling at low periods, and then we've extended it up to, as Yusuf said, up to 20 seconds. So as Yusuf said, we've extended the period set, and we've extended the usable frequency range for many of the records that were in the NGOS1. But I have a graphic to illustrate how that was done. So I have a recording from the Lake Hughes number 1 site for the San Fernando earthquake. And I have on the left an acceleration velocity displacement plot for the time series from that record. In the blue, I have the record that was collected in the NGOS1 project. In the red, I have the record that now is included in the NGOS2 project. So we've extended. Visually, you can see we've extended the time window for this record, but we've also, if you see the bottom plot, the displacement is quite different. So we've refiltered this record, and we selected a different filtering, high-pass filter for this record. So to illustrate what was done in the filtering, I have a pseudo-spectral acceleration plot versus period on the right for those two time series. Same color scheme here. So to illustrate the filter corners that were selected for this recording for the two projects, I have two vertical lines. In the blue dashed line, I have the high-pass filter corner selected for the NGOS1 project, and I have in the vertical red line, I have the filter corner selected for the NGOS2 project. So we've extended the period range for this recording from 1 second to 8 seconds. And so for many of the recordings in this similar data set, we've extended the period range, but there are also some recordings that we had to decrease the period range. So those are listed in the NGOS2 file. In addition to reprocessing all the records, there was a large effort to assign what we call a quality flag for each of the recordings. There was two types of quality flags in the project. One was based on an unpublished report by Bob Dara and Walt Silva. The main idea is that some of the older recordings from triggered stations may have missed the P wave arrival or the S wave arrival. And so I have a graphic on the bottom to illustrate how that could happen. In the same recording that was in the previous slide, I have now the horizontal, 3 horizontal components for acceleration, the 2 horizontal at the top and then the vertical at the bottom. And if you look at the very bottom, you can see the vertical acceleration time series. And then in this time series, the largest amplitude of the vertical component occurs near the start of the record. So based on the methodology that they proposed and the visual check of the time series, they assigned this as a late P-trigger flag. So that means that this record likely missed the whole P wave arrival. The second type of quality flag, what we call a spectral quality flag, that was assigned mainly to the small to moderate magnitude recordings. These were new recordings that have not been looked at before, and so we wanted to make sure that we were collecting the information correctly and processing it in a good fashion. And then I have a graphic to the right to illustrate how this was done. So that's on the left, I have the pseudospectral acceleration versus period for 10 stations for a specific event. And then I have, those are shown in the color lines. And then in black solid line, I have a target or a median for that event from the Chu et al. 2010 ground motion model specific for California small to moderate events. And then we have the 2 plus or minus 2 sigma shown in the dashed black lines. And so the idea is if it falls outside those limits, we need to look at the record again and assess if we've either filtered it correctly or if we had the correct gain or instrument correction information, or if it was even associated with the correct event. So for this methodology, we take this pseudospectral acceleration, we normalize it by peak ground acceleration, and we get the plot on the right, which we call spectral shape. And so each of the spectral shape was visually looked at, and if it falls outside of those limits, we check those standard methods, the standard information. If it was a hard rock site, it may fall outside that limit because it's a hard rock site, and so we didn't want to flag it. And so we did a large set of review, and we've eliminated a lot of these problems in terms of information quality. But the records that are still in the database and are still outside this limit, we provide that flag. So after collecting the database, the records, the information about the event and the site, we had a large team to create what we call the Flatfile. And so this involved all of the ground motion developers and a set of postdocs. And so this Flatfile contains all the key information that are used for the input parameters in the ground motion models, but it also contains information on the station siting and the record quality information, as I showed in the last 2 slides. I'd like to quickly finish up with a summary of what was changed and then what is available on the online peer website. So in terms of metadata, we've added a large set of recordings from a large set of new events. But in addition to collecting these recordings, we calculated a new rotated spectra, or ROT-D50, for 11 different damping levels between 0.5 and 30%. So now there are 11 flat files for the ROT-D50 case. We've also revised in a significant way the existing metadata. For example, we now have a single column of VS30, and we've updated all the site to source distances because of the new methodology for simulating a finite fault. And then we've also removed a lot of co-located records, or records that were 2 records on the same pad for that event. We've only included one of those records, which we thought it was the higher quality record. And then in total, we have a large set of metadata for each of those recordings. In total, about greater than 270 columns of metadata. And so in terms of the flat file, we provide all that information online. And so I have a graphic here to illustrate a portion of that flat file. And then three things I'd like to point out about the flat file. I call these the key linkage IDs. Those are in those specific columns here I show at the bottom. On the far left, in column A, is record sequence number. That's the unique identifier for each record added to the database. And then in column B, we have EQID, or the earthquake identification number, which is a unique identification number for each event. And then on column H, we have what we call a station sequence number, or SSN. It's a unique identifier for each station added to the site database. So the reason for these key IDs is that in addition to just providing the flat files, we also provide the site database. So you can take each of the recordings from the flat file and then get additional information for each of those recordings from the site database. And the way to link those 2 files is this station sequence number. We also provide a finite fault file, which provides all the information for the event, and as well as the event parameters, the geometry. So To take the flat file information and come to this file, you have to have this EQ ID, and that's shown in column A. So finally, after a period of time, in addition to all the flat files, the source database, and the finite fault information, we will be providing all the time series that were processed in the NGOS2 database. And that will be provided at the website, the Ground Motion database website at Pure, and that's shown above, and also the graphic that you guys are probably aware of if you used it, and that will be available within a month or two. Thank you.